So we're gonna move on to a new concept, which is super cool. Okay. So you gotta. We're gonna talk about something that seems totally unrelated to antiderivatives, but over the next couple of days we'll build up this idea. It's really powerful. So the first thing we got to do though is we're going to look at the challenge, kind of the problem we're going to face is how could we add up areas under curves? Okay, so here's the picture I'm going to draw. I'll put these notes online so you can refer back to this picture. But if I've got some function f, and we're going to look at some interval, say from a up to, I better spread this out a little bit. This is always kind of a hard picture to draw, so something like that. So if we're going to go from A up to B, and we want to add up the area under this curve between A and B, well, how might we do that? Okay, one approach we could take is we could break this up into a bunch of rectangles that were either inscribed or circumscribed. Inscribed meaning below the curve, so contained within the curve, or circumscribed meaning above the curve. So we're going to to do this, we're going to slice up this interval from A to B into n subintervals. Okay? And so the first one would just look like this. So here's our slice. Okay, let me do this. I'm going to cheat a little bit and use my vertical slicing tool. So the first one's going to look like maybe like that. Okay, so there's my cut. So my cut is gonna slice the function. So if I'm gonna do like inscribed rectangles, I could take that slice of the function and approximate it by that rectangle that we've inflated from the bottom until it bumped into the function, right, at the left corner. Okay, and we'll do the same thing again and again, all the way up. So then we'll end up with one here that's going to look like that, right? So on and so forth. We'll have one in the middle somewhere to kind of represent just a generic slice, which is going to look like this. And then here's our last one. We'll draw our last two, how about? Okay, and so on and so forth. We just want to add those up. Now, if we wanted to make those circumscribed rectangles, well, that's fine. I could do that. It would just be a matter of maybe we'll make these red. I'll just deflate these from the top until they hit. So I'd add that one little bit of extra area to it at the top, right? And I'd get this red circumscribed rectangle. And this would be the next one. It would look like this, for example, right? See what I'm saying? We'll get back to that. But let's do the inscribed ones for now, okay? So how are we going to do this? Well, if we're going to cut this into n separate slices, right, n rectangles, then what's the width of any one of those going to be? We'll call it delta x. Right, but what's that going to be in terms of my left end point of the area and my right end point, A and B, and the number of subintervals is n. Okay, so if I'm saying that this is delta x, so this is delta x, right? What's that width going to be? How are we going to define delta x? I've taken this whole area and cut it into n equal pieces, equally wide pieces. Divided by n, exactly. Does that make sense? We take the whole width divided by the number of subintervals tells me the individual width of each slice, right? So we could define it as b minus a over n, okay? Well, this function here is f of x. Okay, this is the x-axis. So if I want to come up with, being as this function is monotonically increasing, right? No peaks. It's always going to increase. And so if I want to come up with the height of each rectangle, it's going to be determined by where on the rectangle. Let's take this middle one, for example. The height is determined by the value of the function where?
At the leftmost point.
At the leftmost point, right? So it's going to be the value of the function at the left edge of that subinterval, right? Does that make sense? Okay. So if I wanted to, then I could come up with an expression for the area of each of those subintervals, and I would just have to add all those up. Agreed? Let's call this value right here a. I'm going to call that x sub 0, and I'm going to call that x sub 1, and I'm going to call that x sub 2. And so this one's going to be, b is going to be x sub n, isn't it? Because there's n slices. Everybody agree? So everybody agree? And so this would be x sub n minus 1, and that would be x sub n minus 2, and we'll have a whole slew of them here. Well, this is going to be the ith subinterval. I is the index variable, right? And really, this is the generic one. If I were 1, it would represent the first subinterval. If I were n, it would represent the nth subinterval, right? Because this is the first, this is the second, this is the nth, so this is going to be the ith. Or I could be any one of these values. It's the generic one that could represent any one of them, right? Depending on what the value of I is. So we would call this then, this is going to be x sub what? Sub I. And this would be x sub I minus 1. Agreed? Okay. So then let's come up with the area of the ith subinterval based on the left endpoint. Okay? So if we're doing an increasing function with an inscribed area, the area is just going to be the width times the height, correct? Okay. At the left interval, the height is going to be given to us by the value of the function at x sub I minus 1. Agreed? Okay. So x sub I minus 1 is the height. The width is delta x. So wouldn't that be the area of the ith inscribed rectangle? Everybody agree? Okay. So that's the area of the ith one. If I want to add up the whole area under the curve, then all I would really have to do, the total area would just be the sum of the area of the ith subinterval as we take I to run from what to what? 1 to n, right? That's all that stands for, right? That's the sum of all of these terms such that I goes from 1 to n incrementally, right? So that means literally a sub 1 plus a sub 2 all the way up to a sub n, right? Which is really all we're doing, isn't it? This is areas a sub 1, that's a sub 2, and that's areas a sub n. We're just going to add them all up. Okay? Well, let's do the same thing. So I'm going to call this, well, let's finish the expression here then. So if we want to do what we're going to call the left sum, so we're going to call this a sub L for the left sum. That's going to be the one that's built from the height based on the I minus 1th, the value of the function at the I minus 1th x value on our interval, right? Okay. So what's that look like? Well, then there it is, right? So A sub L is just gonna equal the sum of the height, which is f of x sub I minus 1, times the width, which is delta x, as I goes from 1 to n. How would I change that to get the right subinterval? I want to make that blue. Is there a way I think there is. Yeah, I think I can do blue. Oh, look at that.
Oh, man.
I'm feeling pretty smart.
Advanced.
Okay, so now what if I want to tweak these so all the rectangles are going to be taller? So now I'm going to have them go all the way up to where they're going to be circumscribed, right?
It's just the same thing, but it's just X the height.
Yeah, does everybody see that? It's the same thing, but now all of the rectangles are defined, the heights of the rectangles are defined by their right endpoint on the subinterval, right? And really all I've done, if you look at this, all I've really done is I've taken each one of these rectangles and I've just slid them over one, haven't I? You see that? And I'm going to slide them over one, so I'm going to discard that first blue one, and I'm going to add an additional, right? I'm going to have to add an additional red one at the end. Okay, so that's going to be handy to us later. So then if I want to do those, if I want to calculate, now the ith subinterval is going to change just a little bit, right? Now it's going to become a sub I equals the value of the function at the right endpoint, right? F of x sub I times delta x, right? Okay. And so a sub r just becomes a very similar looking function, only difference being f of x sub I. Okay, good. All right, so let's go back then and let's talk about how we could say what is, for example, what is x sub I? For example, what is that value in terms of, because that's a value, that's not one that's given to us in the original problem, right? In the original problem, the task I faced you with was taking the area from x equals a to x equals b and adding up that area by dividing it into n subintervals. So I would have given you the values of a, let's say that's x equals 2, and maybe this is x equals 8, and we're going to take, I don't know, 20 subintervals, so n would equal 20. I didn't give you something like x sub I. You got to come up with that, right? What's that going to be? What is x sub I in terms of the stuff that I gave you, which is just a, b, and the number of subintervals n? What's the distance from there to there?
Delta xi.
It's just delta x times I, isn't it, right? Everybody see that? Because think about it as steps. I'm starting right here and I'm going to take how many steps of width delta x to get to the right edge of the ith subinterval? Well, that's I steps, right? Everybody agree? So x sub I then should really just equal delta x times n, but I didn't start necessarily from 0. Where did I start from? A. So it'd be that, wouldn't it? You see what I'm saying? Okay. So if we come down here to this problem, we could define x sub I as being a plus I delta x. I said n delta x up there, but it should have been I, shouldn't it? Right? What if we went, what's x sub I minus 1 then?
It's the same thing.
Same thing, but how many steps did I take this time?
I minus 1.
I minus 1 to get to there, right? Because the left edge of the ith subinterval is the right edge of what interval?
I minus 1.
The I minus 1th interval, right? Everybody see that? Okay, so then for this problem right here, I could say, okay, this is going to be the same kind of thing, only this time we would define x sub I minus 1 as being a plus I minus 1 times delta x, right? And that's really all I need. And then we can do some pretty cool stuff, right? So let's take, I'm gonna cut this and paste this, and we'll try one. We'll actually take a specific example and come up with some area approximations, okay? Isn't math just get so cool? I mean, as you can do stuff like this, this is just amazing. I've done this a million times, but it still just gives me the chills to think about being able to do this with math, you know, it's cool.
I wonder if Cooper ever gets the chills from chemistry.
It's,
It gets the chills from the juice.
Yeah.
oops. Okay, so let's do this. Let's actually calculate an area under a curve. Let's take the function, how about f of x equals x squared? Take something simple, and let's add up the area from 1 to 8. Something, right? Let's make something up. Okay. So I'm gonna distort this function so we can see it better, but let's just say it looks like that. Okay, let me draw one more time. Like that. Let's say that's 1, and this is 8. So this is the area that we're looking for right there. Let's calculate this using left subintervals, right? So are those going to be inscribed or circumscribed? They're going to be inscribed, aren't they? Because if I inflate a rectangle from below, it's going to bump into this thing at the left edge first. Agreed? So those would be inscribed. Okay, so if the function is f of x equals x squared.
So the inscribed, does that come from its inside of the curve or inside?
Yeah, inscribed means it's inside the function. So for example, if I were going to, I would say for this circle, the blue square is the largest inscribed rectangle, right?
But wouldn't it be inscribed to the area and not the curve?
Well, inscribed means it's the largest contained within, essentially. So this would be the largest, this is the largest square that I could
Right.
inflate inside the circle, so that's an inscribed
No,
square.
yeah, I work with, for the
Okay.
3D modeling I use.
Okay, and then
I use
circumscribed,
something like that,
so you're familiar with that, so then
Yeah.
circumscribed would just look like,
Exactly.
that would be the smallest circumscribed square, right? And so when we take a left interval here, we're talking about a blue rectangle, not a red one, right? It's one that's gonna be inscribed, and that's gonna be x sub I minus 1, and that's x sub I, right? Okay, but what's that gonna look like then if we're calculating a blue area, a left area, which just happens to be, if this function were 4 minus x squared and the function were decreasing, well then the left interval would actually become the circumscribed rectangle, right? Everybody see that? Okay, and we'll look at one like that. But let's see if we can come up with this area function. So we came up with the generic formula right there, didn't we? So we're just going to plug in the specifics. Well, our f of x is x squared. What's our value of a? 1. Okay, right, everybody see that? That's our a. And we said how many rectangles did I say? I don't know if I said. Let's do 8. I said 8. Okay, let's do 8 rectangles. Actually, I don't want to do 8 because let's do 10. Okay, let's do 10. So if we're doing 10 rectangles then, what's delta x going to be?
2.5.
So delta x is just going to be the total width divided by the number of rectangles, right? So we're saying n, I'm telling you that n equals 10. I'm imposing that on the problem. So then delta x
7 tenths.
would be what?
7 tenths.
Yeah, I wonder if we should, I'm not going to contrive it. I probably could have picked an easier one, but that's fine. So delta x is going to be 8 minus 1, so 7, right, divided by 10. Okay. So 7 tenths. Okay.
How many different ways can you say it?
7 tenths. And our function is then going to become a sub L is just going to equal the sum as I goes from 1 to what? No, no,
N,
Eight.
to 8,
well,
10.
10, right?
Ah.
Because that's how many, we're adding up discrete things. Remember, you guys, we haven't done this for a while, but you did a lot of this last year presumably, right? So when you're doing these discrete sums, then that means you're adding up discrete things. You're adding up areas in this case, the areas of the 10 rectangles we're carving out, right? Okay, so then we're gonna have f of x sub I minus 1. Okay, well, let's figure out what that is. If delta x is 7/10 and a is 1, then x sub I minus 1 is gonna be, what's it gonna be for us? It's gonna be 1 plus I minus 1 times what? 7/10, right? So we're gonna take f of 1 plus 7/10 I minus 1 times delta x, which is 7/10, right? Agreed? Okay, and what is that really? F of x for us is x squared. So it's just gonna be everything inside that function squared, right? And that looks pretty terrible
Until you get your calculator out.
until you get your calculator out, exactly. So that's, whoops, not F. That's gonna be the quantity, 1 plus 7/10, let me make that a bracket instead.
I'll try this break.
1 minus 7/10 times the quantity I minus 1 squared, agreed? Times 7/10. As I goes from 1 to 10. Well, that's a calculator problem. And we could add those up if we want to, it's fine. We could just, because there's only 10 of them,
It's thinking, oh, wow.
I'm serious? Shouldn't take that long.
148.855.
I
Okay,
got
I'm
it.
surprised it took that long.
I had to type it in.
It took a second.
Wait,
Well, no, it
what'd
took
you
a second
do?
for it to load.
What'd you do?
148.855.
That's surprising, that it took a second to load, because that's not that
I
big a
got it.
calculator. I can see if you made n like 1,000, your calculator would probably smoke and short circuit. But it would do it, I think it would do it.
2, 3.
Do you guys see
Oh, I
that?
see what it is.
Do you guys see, we could add this up manually too. It'd be no big deal. We're just
We
gonna let
could.
I run from 1 to 10, and so we could literally add up. We could do something kind of tricky here. Because I've got this 7/10 that's a constant, that 7/10 is gonna be a factor of each of the terms that we create, right? You see that if I added up all 10 of these, I'm gonna get 7/10 times something for I sub 1 plus 7/10 times whatever that gives us for 2. So I could factor that 7/10 out in front of the whole sum, couldn't I? Because it's a common factor. So you see that, and this is just a reminder of, you guys did all this stuff last year, right? Learned the algebra. Okay, so,
We did, technically.
so this, in other words, we could take that outside the sum because it's a factor of each term.
Yeah.
Right? That's okay to do. So that makes things a little bit easier, but then we could add this thing up pretty easily, right? And so like if you were gonna do, a test, like, I'm probably not gonna give you a lot of these just because I don't think there's a lot of value in it, but if you were to take like the AP test, or you'll see this maybe in college, maybe your college professor is hung up on this stuff and wants you to add these up manually. It could happen. It's not hard to do. For small numbers, it's almost quicker just to do it manually, right? So we'd have 7/10 times 1 plus 7/10 times, times
1 minus 1.
1 minus 1 is 0, right? So the first one's just gonna be 0. Plus 1 plus
Wait, wait,
7/10,
whoa.
Wait, what?
It'd be 1.
1, sorry, because it's being squared.
Yeah.
Sorry, whoops, my bad.
Oh,
my bad.
Yeah, but yeah.
I was thinking the picture started at 0. I wasn't even really thinking about the problem. So then we get 1 plus 0 squared is 1, plus 1 plus 7/10 times 1 is 1 and 7/10, so 17/10 plus 17/10 squared.
I'm confused.
So wait, wouldn't the next I though be 7/10?
No, I is
It's just
1,
1,
2,
Oh, yeah,
3,
because-
right? I is
yeah.
discrete, I is the index. It's just counting, what does I do? It's just counting the number of the term you're on.
Yeah.
How did you get
You understand when we say, we throw these words around and it makes perfect sense to me because I've done this in so many different contexts, but when I say an index variable, that might not mean anything to you. What does it mean to index something?
Catalog it.
Catalog it and count it, right? If you're gonna index all your baseball cards, you're gonna put each card in a place and write it down on a list, right? And so you're just keeping track of them, right?
Yeah.
And so an index variable is nothing more than just a counting variable that assigns a number to each one so they're different and where they're recognizable, right? Okay? So there's for I equals, this was I equals 1, that's I equals 2. Third term would be I equals 3. We would just get 1 plus, so we're going to get, what's that? 3 minus 1 is 2. So 2 times 7 tenths is 14 tenths, plus 1 is 24 tenths, right? Squared.
And do you wanna leave it with the tenths on the bottom, or do you wanna simplify?
Well, you just put all that in your calculator. See what I'm saying? It would just be something where you'll just put all that into your calculator and add it up manually. And you're just gonna get some decimal answer, or maybe calculator will give you some fancy fraction. But that's all you're gonna get, right? Because we're just doing this for a discrete number. Now, what if the number of subintervals were 25? Well, you don't wanna add those up manually. I don't even wanna add up 10 of them personally, right? So what we'll do instead is we'll just let our calculator do this. You guys know how to do that?
All right, yeah.
Okay, let's go through that. I'm gonna show you, in case you don't remember. On the calculators, there's a really simple way to do this. Man, I just love this stuff so much.
That was good party math.
It is. This is a well-balanced meal of math protein right here.
Oh, yeah.
Delicious.
Delicious.
Okay, so all you gotta do, if you wanna add this up, is we're just gonna go 7 tenths. So 7 tenths times, and then we wanna do this summation, right? So you go to math, and then I think you just go up from the bottom to summation right there. It's so easy with the new operating system. Look what that looks like. It looks identical to what it's supposed to look like. So we're going to let our calculators, what's the only variable that's convenient on our calculators? X. So X becomes our index variable. So we'll let X go from 1 to, in this case, what? 10. Good. And then we're just going to input, we already took the 7 tenths out front, right? We're just going to input this stuff right there. So it's just going to be the quantity 1 plus, I'm going to put the fractions in parentheses because that's a safe thing to do. Then you know they're being treated as numbers. 7 tenths times the quantity X minus 1. And that whole thing is being squared, right? So I think I need, I think I forgot a set of parentheses, didn't I?
You don't even have to worry about the parentheses if you do the alpha
Do you have
F1.
an alpha?
Yeah, I know. Yeah. So I'm going to go ahead and I'm going to insert, you see that you got to be real careful with the parentheses. I'm going to insert another set of parentheses because I have to have the parentheses for the argument in the calculator. It's expecting everything you're inputting into the summation algorithm to be contained in a set of parentheses. Second right gets me all the way over to the right. And so this is going to be the set of parentheses that's squaring everything within. And here's the set of parentheses. Is that wrong?
No, that's wrong. You have to do one more.
1, 2,
Square
3.
one.
Oh, I did, don't I? Yeah.
You did, don't you?
I did, don't I? Yeah. So that's going to be delete. So there's 1, 2. No, that's right.
It's
Oh, no, yeah,
No,
that's
it
right. No,
was-
you were right.
I think I was right.
Yeah, you were right. It's just,
It's just looking weird.
it looks weird.
that in parentheses was the one that was.
1, 2. Here's how you can keep track. You just go 1, 2, 3. Subtract a 2, 3, 2, 1. And then that should be.
Yeah, no, I think you were right the first time. You just needed parentheses.
Yeah.
It just,
just does that because the squared's there. I
Well,
think.
yeah, it's supposed to do that, it's just that the one on the far left is also supposed to do that.
Yeah, that's why I don't understand why it's not.
That's to there, that's to there, that's that.
God, these are so hard to count. Okay, maybe it is
No, no.
easier to go ahead and use.
Yeah, it
I'll
is
try
a
it.
lot easier.
We'll see if
So
this.
like, yeah, just hit enter.
Oh,
I
see,
know-
it was
I know
off.
what's wrong.
There it is. That one's wrong.
That parentheses that you have, that one right there, that one was part of the original thing, so you need to put one right there.
Oh, yeah.
You see it? Explain that to me again.
So you used the one that it made for
Yeah,
you
so you need
as
to
the
go-
one
Oh,
that-
yeah, yeah.
One,
I
and
thought I
then
just put an additional one in there, but didn't I go back and insert one there?
No.
It didn't stick, because I meant to do that. Right? That's why I hit second insert, and I put one in there. I swear I did, but it didn't stick. That's what happened.
So
You're right.
that, so then you square right there,
Squared, and then close it.
No, you
Yeah, well, just hit
you
enter
didn't-
and then quit, and then do it the fraction way. Okay?
Or.
But how is that not right? That's gotta be right.
Well, it's just an argument, okay,
Can
so
I-
like, when you first input the sigma notation, or the summation, it pre-creates both of the parentheses,
I
unlike
gotcha.
some other things. So what you're doing is you're using one of the wrong parentheses
Oh,
somewhere, and you just
I
don't know
gotcha.
where,
Those
because
parentheses
there's
are
no
okay. That
difference
I
one- that
gotcha.
one-
visually.
That one's good.
So I'm gonna delete everything.
Yeah, just get rid of it, and then do fractions.
Yeah, so there, I get it.
Yeah.
See, I see what I did. I gotcha. I gotcha. Jeez.
Remember.
Okay, now what I'd have to do is set up a set of parentheses there.
Occam's razor.
Yes.
Simplest is always the best.
So we'll go ahead and
Wait,
do.
why are you already doing one?
No, I don't want one yet.
Oh jeez, you're all turned around.
Jeez, I'm so turned around.
This
Discombobulated.
good math is gonna show.
Discombobulated is the great word for this. That's what I am.
So, yeah, go in there, and then parenthesis,
So I need.
one parenthesis.
No, I. Oh, I do. You're right. I
One
do.
parenthesis,
I need one.
And then one plus.
1 plus alpha f1 fraction template 7 tenths. Come on. Times.
No, don't do parentheses, don't do times. You're just boggling it all up.
No, it's fine. I gotta
I
do
mean,
7
it is
tenths.
fi- It is fine, but it's boggling.
Just do parentheses.
X minus 1, right?
Parentheses.
Parentheses.
One
Squared.
more. Now squared.
Ah, ta-da.
Now put
Okay, it's gonna
See, yeah, it
think.
takes a
There it
second.
is.
See-
Whew. Okay,
Alright.
148.85.
Yeah.
Okay,
that's what
good.
we got.
All right.
Yeah.
Okay, so
It's clear.
here's the point I want to make though. Are we gonna have time to finish this? How much time we got?
10.
Okay, I think we can do it.
17 more minutes.
17 more minutes.
Oh,
Okay.
I was talking about that.
Oh, talking about basketball. That's not what I was asking about. Okay, so what about let's now calculate the circumscribed rectangles, right? So that's no harder to do. It's the same, in fact, it's actually easier. The formula is easier in this case because they're the right rectangles and the right ones are easier than the left ones. You'll see why.
Can you just go into the summation that you already made on your calculator and then just delete the minus one?
Okay, I can. I can.
So you can or can't.
I can. I can.
Like
So do you see then that down here, the right, that's what it's gonna amount to on the calculator, but I want you to see it up here.
Okay.
So A sub r then is just gonna equal the sum from 1 to 10 of f of x sub I. But what's x sub I? X sub I is just A plus I delta x, right? So for us, that's gonna be the quantity 1 plus I delta x is just 7I over 10, easier, right? See what I'm saying? You don't have to have that extra set of parentheses, which caused me so much grief, right? And that whole thing is gonna be squared. And then I've got my 7 tenths that I'll just pull out front because that's being multiplied by a constant, no I in it, so I can take the constant out front, right? So this is the sum that I'm going to add up on my calculator, which gets a lot easier, okay? So we can go back in and I go, oh gosh, what am I doing? I'm panicking, gotta get through this. So if I go up and grab this thing, Okay, there it is. All I've got to do is I've just got to make this, I can delete this whole thing. I mean, you see what I'm saying? I didn't have to, but I can. I can just go up there and make that a 7x
Yep.
on
Maybe
top,
one more parentheses.
right?
One more parenthesis. You have to delete one of the parentheses.
Oh.
Right?
Say yes. Just go
I don't really have to, do I?
Well,
Oh, yeah.
probably.
Yeah, I do.
Just
So I need to
Just
delete
say
that
yes.
one.
Just say no.
I'm gonna do it with 1,000 total things.
Okay, see that? And so if I hit enter then,
Guys.
it's going to think for a little bit, and my answer is 192.95. Well, let me ask you this. Where do you think the actual area falls?
In between that.
Yeah, in between somewhere, right?
170.905.
Okay, so can you think of a way that if we wanted to make an estimate of the actual area, how could I get a more accurate estimation? Because that's a pretty big range of differences. What do you think?
Wait,
Like divisions.
Yeah, more divisions, because look what happens. Look what happens if I increase right now, the difference between the inscribed and the circumscribed rectangles are pretty significant, right? The sum of all those boxes is going to be a big deal, right? But if I make those shorter intervals, it matches the area better, doesn't it? Right? If I took this interval and instead I made it a bunch of really small intervals, well now, man, it's hardly even perceptible, the difference between, I can't draw it very well, but you see, the difference between the actual, the inscribed and the circumscribed becomes much less significant, and I'm pinching the area more tightly, right? We can see that. I've got some cool little applets that I'm going to put on the site, on the Moodle site, that you can play with at your leisure, but I'll pull one up.
I did it to 100 places, up to 100 places, and it took me 65 seconds.
65 seconds. Yeah, that's
Do
a
1,000. Or, I mean, 1,000. Yeah, that's what I did, 1,000.
Now do 10,000.
Yeah, hard pass. Although that'd be interesting. You still need.
Where did those go? I lost a bunch of my.
Oh, no,
In my
no,
jokes
no.
folder? You think it's in the
Yeah,
jokes
I think it's in
folder?
the jokes
Uh-huh.
folder.
I think it's in calculus. If I go in here, I bet I've still got those links from last year. So if I go to.
Spicy. Pretty spicy. Are those all your tests?
Yeah.
Mary what?
Merry Christmas. Does it say Mary looking at the jokes folder?
No.
We like talk to IT.
Gosh. Every year when they ghost our machines, I lose a bunch of these things, and it drives me crazy. Okay, here's a good one, though. This will work. Here, just look at this. So let's take an area. This is pretty cool. Let's take an area. We're going to go from x sub 1 equals, how about if we add the area up from 0 to 3. And we're going to take the function y equals x squared, and we're going to use lower limits. That's fine. And we're going to choose the value of n.
Right there.
Right there. Watch what happens. If I let n equal something big, it doesn't match very well. But if I let n equal something really small, like 40, look how closely it matches. Now I end up getting the area under the curve being approximately 8.667, right? If the actual area works out to be 8.993. Look how much that diverges if I take fewer rectangles. I get much further away. Let's take the upper sum, and we see the same thing, right? It's going to approach much more closely the actual value, right?
Oh, it's.
If we let the number of rectangles get large.
Why does the exact value value change? whether-
It shouldn't. I don't know why it did. That's,
Yeah. What?
yeah, it shouldn't. Okay, so I think we need a better apple. Let's find a better one. Uh,
I'm not doing 10,000.
You are? Oh my god. Rip. So what kind of new guy